Welcome to Grade 12s. It is Physical Sciences time on a Saturday. I am Looney, and joining me in studio today is Phil. Phil, how are you doing?
I'm great, thanks, and you, Looney?
I'm good, thank you. So what are we doing for the Grade 12s today?
Okay, well, we're going to be taking a look at some wave, sound, and light. We're going to be doing some Doppler, we're going to do some diffraction, and maybe even some photoelectric effect.
All right, Grade 12s, you heard it. We've got a lot of stuff for you guys going on. So I hope you've got your pens and you've got your notepads and you're writing down everything. I will post as much as I can from the notes. So do remember to go onto our Facebook page, which is facebook.com/learnextra. You can hit us up on Twitter as well. Our handle is @learnextra. You can go download our show notes on learnextra.co.za/live. Remember, guys, we do have curio going on. If you answer all the questions and submit them, we will go through them at the end of the show. We will post the code on our Facebook page, so make sure you do look out for that. But with all that said, Phil, I think it's time we take it away.
Absolutely, thank you so much, Looney. Okay, well, as we said earlier, we're going to be taking a look at some wave, sound, and light. Now, matrix, this is a section that you can score some really good marks because the questions are all very much similar to each other. And guys, if you're going through past paper questions, especially like the ones that we're doing today, guys, it's going to prepare you very, very well. And it's a section that's easy to get those marks. So it's all down to a couple of basic concepts. We're going to be giving you some tips on how to solve some Doppler, some diffraction, and some photoelectric effect, because very often these are sections which are tackled right at the end of the matrix syllabus. Now, matrix, if you haven't seen this section before, that doesn't mean that you can't learn anything. Guys, get a pen and pencil together, go to the Facebook page, get those notes, and actually log on to Curio. Now, Curio is a fantastic thing that we starting to get going again. And guys, please, if you missed the maths show, Curio is up there and you can still do the maths questions. Life sciences, guys, there's still some questions up there, but we're going to be talking about some physical sciences for the next couple of minutes, and hopefully getting onto that page, answering some of those Curio questions. Okay, so matrix, for those of you that have or have not done this section, well, let me introduce it a little bit. We're going to pretend like you haven't done it before and just reteach the section, because I know that Doppler can be quite confusing for a lot of you. Okay, so we're going to start off with some basic past paper questions, some very typical past paper questions, and this one was taken from the February 2009, and it's question 7 in that paper. Guys, again, get some of these past papers, practice them with us, write down these questions, and especially draw the diagrams and do the equations with us. Okay, so now, as I said, here we go. We've got some Doppler questions. Okay, so now this first one is talking about some dolphins which are swimming under the sea. Now, dolphins are especially different to most other sea animals because they emit a large amount of sound. And this is the way that dolphins find out their environment, they find out where their food is, how deep the water is, and they even communicate with each other using sound. So here we go. They use ultrasound. Now, if you remember from grade 11, ultrasound was sound which was beyond normal human hearing, and we'll see now why. Now, they use this to scan the environment. Now, when a dolphin is 100 meters from a rock, now that might be important. So this rock is 100 meters away from the dolphin. It emits ultrasound waves of frequency 250 kilohertz. So now that's quite important. This is the sound which is coming from the dolphin. Now, if you've done Doppler before, this is called the frequency from the source. It's Fs in the equation. So they've told us how much frequency, or at least what frequency, is coming from the source. And the dolphin is the source of the sound. This is where the waves are actually coming from. So 250 kilohertz. Now, guys, that is far too high for a human ear to hear. We can only hear up to around about 20 or 21 kilohertz. So dolphins have got some pretty amazing hearing. Now, it says while swimming at 20 meters per second. Now, that's also very important. This dolphin is capable of emitting the sound while swimming forward at 20 meters per second. Now, this dolphin is swimming incredibly fast towards the rock. I'm assuming that it's chasing something. So assume that the speed of sound in water, now remember, guys, speed of sound is dependent on the medium. Now, inside water, it's going to travel at 1.5 kilometers, or at least 1,500 meters per second. So now that's the velocity of the sound itself. Now it's asking us to calculate the frequency of the sound waves detected by a detector on the rock. Okay, so now this is quite important. Now, here it is. Let's just do a little bit of revision of what the Doppler effect is. The Doppler effect is a change in the observed frequency. So in other words, the change in the frequency which something hears because the source and the observer are moving closer to or further away from each other. It's because of a difference in their velocities. The rock is stationary, This dolphin is swimming towards it, so the source is moving and they're getting closer together. Now, what's going to happen is the frequency which is measured at the detector will be slightly different to the frequency that the dolphin gives out. The dolphin gives out 250 kilohertz. The rock is going to receive or experience a slightly different frequency. And that's the first step in solving any sort of Doppler. Does the frequency increase or decrease? Now, guys, I'm just going to draw a very, very rough picture of what's actually going on here. So what's happening is we've got a source of our waves. And what's happening is there's this rock which is going to be receiving the waves. So let's say that that is my rock, because my rock doesn't look very rock-like. Let's just label it. So we've got the rock and we've got the source, and this is my dolphin. Now, just remember that when a dolphin is chasing its own waves, what's happening is that these waves will get closer towards each other. They're going to be squeezed because the dolphin is not allowing them to escape. So as it gives out these waves, it's squashing the waves in front of it. So what we're going to find is that the spacing between these waves will be slightly smaller. Now that should give you an indication of whether or not the frequency will be higher or lower. Now guys, how do I relate frequency and wavelength? Remember, my wave equation says that V is equal to frequency times lambda, which is the wavelength. So how would you relate frequency and wavelength? Well, if we rearrange this equation, now guys, this is getting quite theoretical, but it's meant to educate you right from the start. Here it is, that frequency and wavelength have got an inverse relationship. So the inverse of frequency is proportional to wavelength. Now, for those of you that are not too keen to do way too much maths and you're a little bit tired of maths, basically this means the shorter the wavelength, the higher the frequency. So there's step one in my Doppler. I know that the frequency that is listened or observed will be greater than the frequency of the source. So I know that the rock will receive a higher frequency than the frequency of the source. I've already got the frequency of the source. It's 250 kilohertz. Now step two is to change my Doppler equation from this very, very long and complicated one into a much, much simpler one. Now let me give the Doppler equation to you in its simplest form. So here we go. The frequency which is listened or observed, sometimes there's a slash with an O, is equal to. Now here's where a lot of grade 12s get a little bit intimidated, because there's all these signs all over the place. There's two V's, but now on top it's plus or minus velocity of the listener, and at the bottom it's plus or minus velocity of the source. Now this entire thing is multiplied by frequency source. Now the question is, how on earth do I choose a correct form of this equation? It's to do with step one. This is the really important part. I need to change my equation so that step one is true, so that the frequency of my listener will be greater than the frequency of my source. Now, how do I do that, guys? Now, it's actually really quite simple if you look at it in terms of the Doppler equation. The thing which changes my Doppler equation is this fraction over here. I need to change this fraction to my needs. I need to make sure that this fraction will multiply frequency source by a number bigger than 1. Now you might say, okay, well, how can I predict this? There's no numbers yet full. Let's just hang on a second. What we've got to do is make sure that this fraction gets bigger. That's it, guys. Now, whatever I choose for pluses and minuses, this fraction must get bigger. Now, here's what I'm going to do. What I'm going to do is I'm going to change my equation. My Doppler equation is now going to simplify. And here's how I'm going to do it. I'm going to rewrite it and explain it slowly as we go. So we want to find out frequency listened. Now remember, I told you that this fraction must get bigger. Now for anyone that hasn't done Doppler before, these first two V's mean the velocity of the wave. VL and VS deal with the objects which are moving. Now lucky for us, the rock is the listener. There's a detector on the rock which is a listener, and lucky for us, rocks don't go anywhere very quickly. So this rock is not moving at all. So at the top, there's plus or minus 0. Doesn't really matter if you're plus or minus 0, because plus 0 or minus 0 is going to be exactly the same answer. Now here's the trick. At the bottom, now my tricks, I'm going to do this twice and I'm going to say it really slowly. How do I choose my plus or my minus Vs? Now remember that this is my velocity of the dolphin, velocity of the source. How would I change this fraction by changing, now here it is, the denominator. the bottom piece of the fraction. How do I change the bottom piece of the fraction so that the fraction gets bigger? Now think about this. How do you change the underneath of a fraction so that the entire fraction gets bigger? Now, if you start thinking about this, you start off with your fraction, you say, okay, well, if I change the bottom to change the fraction to get bigger, if you take away from the bottom, your fraction gets bigger. So now let me just let this settle for a bit. If I start taking away from the bottom, the entire fraction gets bigger, and that's what I want, guys. This fraction controls my frequency listened. I can't control the frequency source, the dolphin does. So this fraction will allow me to increase my frequency source by multiplying by a bigger fraction. It's all about this fraction, guys. That's the hardest part of Doppler, but you must predict first. So now, this is not the be-all and end-all. And grade 12s, if you're like, oh, Phil, I don't like fractions, please help me, and let's find an easier way. I'm going to show you a slightly easier check right at the end, and it's easy to see if you've gone wrong. Okay, so there we have it. We've got a slightly simplified Doppler equation. We got rid of some of the confusion with pluses and minuses, and we've got frequency source. Now comes the easiest part. The easiest part of a Doppler equation is, of course, to substitute. But as always, I tell my matrics this. Please, the setup, the preparation for this is by far the most important part. So now let's find out what the frequency listened actually is. So I've got frequency listened over there. That's what I'm looking for. Let's substitute in my V. My V is my velocity of sound in water. Guys, please don't substitute the number for air. They will give it to you. So there's 1,500. Now at the bottom, it's the same velocity, 1,500, except now what I've got to do is subtract from it the velocity of my dolphin. And that was 20. Guys, please make sure that you understand why I'm subtracting 20 and not adding 20. This fraction itself is going to be larger than 1, and that's exactly what I want. Now, frequency source, guys, they've tried to trick you. They gave you the source of the frequency in kilohertz. Kilohertz means thousands of hertz. That means times 10 to the 3 or thousands of. So I've got to substitute correctly as 250,000 hertz. Okay, that's very quick vibration. Okay, so now let's just jump onto our calculator. Let's clear off the maths guy's calculation, and let's do the substitution together. So there we've got, okay, setting up our fraction on our wonderful Casio calculator. There we go, 1,500. Go down to the bottom, make sure that you've got 1,500 minus our value of 20. Okay, now, just to show you something, I want to show you what happens when we put in this. Take a look. We've got a fraction which is larger than 1, and that's exactly what I want. Guys, if you want to see just a fraction, just to see if you're doing the fraction correctly, check that this number is larger than 1 if you want the frequency to increase. Now, I just want to show you what happens when you say plus instead. Take a look. Our number is less than 1 there. So we know very quickly if we've chosen the wrong plus or minus. So we know that this is a minus over there, so that's a minus. Okay, so now what I'm going to do, just to keep things separate, is I'm going to make this into fractions, and these fractions are going to be in brackets. Guys, I like to keep things separate with brackets. It just makes sure that I know exactly where everything belongs. So 250,000 hertz, there we go, 250 kilohertz. Fantastic, and we should get a frequency which is larger than our original. And guys, there it is, 253,378. So there we've got 250,000, 53,378 hertz. Now guys, you can change that into kilohertz if you really want to. If you want to divide it by 1,000 to get back into the same unit that they gave us. But guys, please leave your original hertz there because they're looking for your SI units. So 253.38 kilohertz. There it is. Guys, just one last step for the Doppler. Check to see that it matches your prediction. Guys, was 253 kilohertz larger than my original frequency? Yes, it was. Okay, so the frequency which was observed was much higher. If it's wrong, it's very likely that you've chosen the wrong plus or minus. It's that simple. So guys, please don't put pressure on yourself. Is it plus, is it minus? And get yourself into a big stress ball. There's a very easy check right at the end. All you've got to do is say, okay, well, does my answer make sense? And that's good advice for any physics equation. If you've practiced enough, you'll figure out if you've got the right expectation. You say, hey, wait a minute, those numbers don't make sense. Go back, check your substitution. And more importantly, guys, I can tell you now that like 30% of your mistakes in physics are all to do with signs. And here we go. So if I chose the wrong sign, I will get a number which is lower than 250. And that means that I need to go back to my Doppler equation and make a quick change. Fantastic. Okay, right. Well, now this question has got a couple of pieces. And this next one I particularly like. What we're going to do now is we're going to see what happens if this dolphin approaches the rock. Now remember, it was at 100 meters, gave out the 250 kilohertz, and now it's moved onwards. Now it's a little bit closer. Now it says when the dolphin is 50 meters from the rock, another ultrasound wave of 250 kilohertz is emitted. How will the frequency of the detected sound waves compare with the answer calculated in the first question? Now guys, what I'm going to do is we're going to go to a short ad break. I want you to jump onto the Facebook page. Start debating this question. Is the answer higher, lower, or does it remain the same? So this dolphin's giving out another wave, same frequency, but it's closer now. So guys, I want you to jump on that Facebook page, debate this on Twitter, interact with us, guys, and share those answers. What do you think?
All right. Guys, you heard Phil. Debate about that question, guys. Is it higher, lower? Does it remain the same? I remember these type of questions when I used to do physical science. So it's quite interesting, guys. Go on to Facebook and Twitter and tell us what you think, guys, and ask us as many questions as you have. But we'll be back straight after this break. Welcome back, Mindsetters. We are doing physical sciences with Phil. And I did post the question that he's doing on our Facebook page, guys, so you can go through it as Phil is working out the answers. So make sure that you're interacting with us on Facebook and on Twitter. Our Facebook page is facebook.com/LearnExtra, and our handle on Twitter is @LearnExtra. Ask me any questions that you may have, guys, and I'll answer as many as I can during the break, and then Phil will help us with the questions. So far, I think we can carry on.
Thanks so much, Looney. Okay, well, guys, before we went on the break, I was telling you about Curio, and I can actually see on the website some of you guys are starting to answer the questions on Curio. Now, just a reminder, if you missed the maths show, get onto those maths questions. Get onto the life sciences questions, which are still up as well. But, guys, please make sure that you go through all the questions, and right down at the bottom of the page, it says submit. So make sure that you've gone through all of them. And the cool thing about that is it's going to tell you exactly what you got right and wrong. Now, you can redo them until you get everything right and make sure that you are absolutely perfect with these questions that we've posted up. I've taken a look through them, and we'll take a look through them at the end of the show. I think they are fantastic questions. They really sort of get down to the ideas that you need to understand for some of the wave, sound, and light. Now, please, there's just a couple of short questions. Go through all of them, select your answers, and then click submit right down at the bottom, and we'll give you instant feedback. Guys, this is like free testing, but it's not even for marks. It's great for you learning. Guys, please, just a reminder that physical science is not something that you can watch. You cannot just go, oh, I just watched this on TV and feel like I'm learning. It might feel like you're learning, but guys, as soon as you go and you go have your Saturday lunch or sleep this afternoon, it's all going to disappear unless you're practicing with us. So like Looney says, get onto the page, write down these questions, practice them with us. So here we go. We're back into this question that I left with you just before we went to the break. Now, when this dolphin is 50 meters away, now this dolphin has gotten closer. So now, there it is, 50 meters. The dolphin was at 100 meters from the rock. Another ultrasound wave, so a second one, is emitted. How will the frequency of the detected sound waves compare with the answer calculated in the previous question? Now remember that we calculated 253 kilohertz at 100 meters. Write down only higher, lower, or remains the same. And I'm hoping that Looney's seeing you all answering this question on the Facebook page. Are they busy interacting there?
Yes.
Fantastic. Okay, guys, it's great if you're sharing your answers and debating and sharing your ideas on how to do this. So here we go. Higher, lower, or remains the same. Now, before I give the answer to you, I want you to think. And a lot of you are saying, no, Phil, just give us the answer. But I want you to think about how Doppler works. Now, Doppler works according to this equation where we've got a frequency of your listener, which is decided by two things. First of all, the velocity of the sound wave. Now here, plus or minus the velocity of the listener. Okay, the listener was a rock which wasn't moving, 0 meters per second, plus or minus the velocity of the source, which was the dolphin. Okay, now multiply that all by the frequency of the source. Now guys, take a look in this equation. There is no displacement, there is no distance inside this whole equation. It's only velocity and frequency which makes a difference. So guys, as long as this dolphin is still in water, as long as it's still giving out 250 kilohertz, the frequency which is observed by the rock will remain exactly the same. It's not dependent on the distance from our dolphin to the rock. Okay, so I hope that you understand this. I hope that you've gone through your 4 Doppler steps. First of all, make your prediction. Second of all, change the equation to fit your prediction. Then substitute, and then check. So there's 4 really great steps to solve a Doppler equation. So predict, change your equation, substitute, and then eventually check. So it's a very nice, foolproof way of making sure that your Doppler equations are absolutely correct. And guys, this is worth what? 7 marks out of your physics exam that you can guarantee, and that's fantastic. They will always ask you a Doppler equation. They are in every single exam. There is a Doppler in all of the past papers. So make sure that you're okay with this equation and what it means. One equation guaranteeing you 7 marks, that sounds like a pretty good deal to me. Now, we've got a couple of other Doppler equations, and I just want to give you a heads up on what we're doing a little bit later on in the show. So we're going to do a little bit of an ambulance question. I'm not going to do this right now. Now, this is a particularly nice one from February 2010, but what I'm going to do is I'm going to jump forward a little bit. Now, what we're going to start doing now is another wave, sound, and light question. Now, I particularly like this one. Now, this one starts to talk to us about work functions. Now, when I see the word work, I get a little bit scared, but when I say work function, here we go. Work function is to do with the photoelectric effect. Okay, and here we go. So a photoelectric effect. Now, you might say, okay, well, why do I even need to know about the photoelectric effect? Okay, well, first of all, the photoelectric effect is hugely important. If you've been following the news, what's actually started to happen is photoelectric effect is one of the ways that you can generate energy using solar panels. Now, you might say, okay, well, no, at the moment, we're way on beyond that. But there's actually 2 massive photoelectric plants which are going to be installed. One is actually on Gauteng's government roofs, and one is going to be in the Northern Cape, and they're going to be generating huge amounts of power. Now, if you've been experiencing blackouts and Eskom struggling to supply enough power for South Africa's people, the photoelectric effect is one of the ways that we can turn sunlight, which we've got lots of, into electrical energy. Now, this also was the reason that in 1905 Einstein won the Nobel Prize, and that was due to his work on the photoelectric effect. Basically, he proved that light was also made up of particles as well as being a wave. Now, that's one of the potential exam questions. Okay, so let's look at our photoelectric effect. Now, it says the work function of 3 metals is shown in the table below, and here they are. I've got some aluminium over there, so let's just highlight them and find out what's going on there. I've got aluminium, I've got zinc, and I've got silver. So there's my 3 metals. Now let's just remind ourselves what a work function actually is. Now a work function is the minimum energy required for a photon to remove an electron, to eject an electron from a surface. It's usually a metal. I want you to think about why a metal always. Why am I comparing metals? Why am I not talking about carbon or phosphorus or some other non-metal? The reason is metals like to lose electrons. Take a look on your redox table. If you've been linking this up with chemistry, metals like losing electrons. Now, here's how difficult it is, or here's how much work I have to do to remove an electron or to eject an electron from the metal surface. Here we go. Now, to eject an electron from the surface of aluminium, it requires 6,54 times 10 to the minus 19 joules. Okay, so here's my work function measured in joules. Sometimes it's measured in electron volts, but we'll discuss that if those questions come up. Here we go. Zinc requires slightly more. That requires 6,89 times 10 to the minus 19 joules. What about silver? Silver is even more difficult to remove electrons from. Now here's a question. It says, give a reason why different metals have different work functions. Now, if you've been listening very carefully, you could actually figure this out. Why is it more difficult to remove electrons from silver than it is from aluminium, say? And this is exactly it. They're looking for your understanding of what the work function actually is. what you can say is you can demonstrate your knowledge of the work function and say some metals require more energy to remove electrons. So there we go. So some metals, and specifically silver in this case. So some metals require more energy to lose or eject an electron. And that's exactly what they're looking for. They're looking for the word energy to eject. Energy to eject electrons. Because they're trying to hold on to their electrons. Electrons need energy to leave an atom. And this is the amount of work which I need to do to pull them off. So eject electrons. So there we go. That's what they're looking for, guys. They're looking for the amount of energy which it requires to eject an electron. Now, here's the interesting part. Now, I'm told that monochromatic light, now that's quite a difficult word. Let's just talk about it for a second. Monochromatic light. That's light which only has one color or wavelength. Now, how do I get that? There we go. Mono means single or one. Chromatic, both of these are Greek references for one color. So monochromatic means one wavelength or one frequency of light. So a good example of a monochromatic light, I'm fairly sure that you've all seen like laser pointers and you've actually seen something which shines with only one light. That is a light which is monochromatic, of one single color. Now it says it ejects electrons from a zinc plate. Now that's quite important. This light ejects electrons. That means that it's doing the photoelectric effect from a zinc plate. So it's pretty important that it's got enough energy to eject electrons from a zinc plate. Now, it's asking us quite a conceptual, quite a difficult question. Now it says, describe what happens on the surface of a zinc plate when the intensity of the source increases or decreases. Intensity. Now this is to do with whether or not we're thinking of light as a particle or light as a wave. Now, since we're doing the photoelectric effect talks about particles. Okay, now think about this. So describe what happens on the surface of the zinc plate. Now, let me just draw this out, because I like drawing. Even though I can't do it fantastically well, I like to visualize what's happening. So here we've got my zinc surface. In comes in my photon of light. So very often it's drawn as a squiggly line to represent that it's still got some sort of wave property. But basically what I'm trying to say is that I've got a photon of light with HF energy. Now that's Planck's constant times the frequency of the light. That's how much energy the photon has. Now I'm being told that each little photon of light, which is a particle, comes into the surface of the light, it gives away its energy to the electron. So what happens is at the surface, I'm going to eject a photoelectron. That's an electron which has been kicked out or shoved out using light. So this photon had enough energy to do that. Now intensity, when you start to talk about particles, intensity increasing means more photons. More photons. Okay. Now what I'm going to tell you now is that these photons already have enough energy to kick the zinc plate off, or at least to kick the electrons off the zinc plate. So when I increase the number of photons, each photon makes an electron. So if there's more photons, there's more electrons. If there's less photons, there's less electrons. But, quite importantly, these photoelectrons, these electrons which are kicked off, will have the same amount of energy. Remember that their energy depends on the energy of the photons, not how many photons there are. Now guys, that's been full of technical speak. So what I'm going to do is I'm going to go back and we're going to start taking a look at some of the words that I used. So here we go. One photon, one electron. That's quite important. Each photon manufactures only one electron which it gives off the surface. So here we go. These photons come in and they kick off a photoelectron. Now if I've got more photons, I'll have more electrons. But here's the second thing that I talked about. Each photon carries with it the same amount of energy. Doesn't matter how bright the light is. Doesn't matter how intense the light is. Those photoelectrons are going to have exactly the same amount of energy as they did before. So that's hugely important to realize. One photon makes one electron. And guys, that actually proves the particle nature of light. Now, this is why Einstein actually won the Nobel Prize, because he actually proved that light had a particle nature as well. And he proved it using the photoelectric effect. The maths that he came up with actually proved that light behaved like a particle. It delivered light in small packages. And these packages were called photons. Now you might say, okay, well, what's the big deal? Well, guys, photons are called quanta. If you've heard of quantum physics before, they're actually starting to talk about these little packets of energy and how they control matter and light and electromagnetic radiation. Guys, these photons are the beginning of some quantum physics, which is really cool. You guys are doing some really amazing physics. Okay, so here we go. These photons, they come in, they deliver their packets of energy. The electrons are kicked off the surface, and that's where you get electricity from in a solar panel. But now it's important to realize, unless you change the frequency, you don't change the energy of that electron which comes off. So this little electron which has flown off, there it is, it's going to have the same kinetic energy, unless you change the frequency. But we were told that the frequency stays the same. Monochromatic told us that. All that we changed was the number of photoelectrons. Guys, they will ask questions like this. What happens if I change, first of all, the frequency or the intensity? Okay, guys, please be prepared for them, because you've actually got to understand what this really means. Okay, so let's move onwards with this question. Okay, now we're back to our question with zinc, aluminium, and silver. Now this is really cool. I really like this question. It says monochromatic light source ejects electrons from the zinc plate. So we know for sure that the energy of the photon, now this is the groundbreaking part of this, that the energy of the photon, okay, it's got to be greater than or equal to the work function of zinc. I know that each photon has enough energy to kick an electron off the surface of zinc. That's what this really means. This is telling me that the photons have enough energy. They meet the requirements. Now, here's where it gets tricky. It says, describe what happens when the same light when the same light source shines onto a silver plate or an aluminium plate. Now, this is quite difficult. Now, what I want you guys to do is, since I've stated the question already, what I'm going to ask you to do is to use the values here. I want you to use the values for silver and aluminium and the work functions to tell me what's going to happen when these same photons with the same energy shine on a silver surface and then on an aluminium surface. So guys, get debating, get onto the Facebook page. Guys, complete your curios and take it away, Looney.
Okay, cool. Guys, it's so great to see all of you interacting on Facebook and just answering the questions that Phil is asking. I'd just like to send a quick shout out to Brilliant, Dashan, Mosa, and Bongekile. You guys have been great on the page, answering the questions and actually interacting with us. So that's great, guys. All of you mindsetters, join us on the page because it's great. We're having fun on physical sciences. So we'll see you straight after the break.
Grade 12, Saturdays on Mindset are exclusively for you. Join us this coming Saturday for lessons in maths lit, physical sciences, life sciences, business studies, geography, and accounting. Don't miss out.
Welcome back, Mindsetters. We're still doing physical sciences with Phil. Thank you so much for hitting us up on Facebook with all your questions and all the answers that you've been giving. So I'll take it straight back to Phil.
Thanks so much. Okay, well, what we're going to do now is we're going to answer that question that I posed to you before we went to the break. Just a reminder of what it said. We had these photons, which were good enough, had enough energy to get energy to kick electrons off the surface of zinc. Now it says, describe what happens with the same light source. The same photons shine onto a silver plate and then onto an aluminium plate. Now, to answer this question, we have to go back to our table, which shows us the work functions. Now, think about this. These photons had enough energy to kick off electrons off a zinc plate. They had more than that. So the energy of the photons exceeded this value. They were greater than or equal to that value. So now, what happens when we shine these same photons onto a silver plate. Now take a look at this. A silver plate needs a lot more energy. Now, one of two things can happen on a silver plate. So the first option is that no photoelectrons, no electrons would be ejected. So no photoelectrons would be ejected. Now, why would that not happen? Because silver needs more energy to kick electrons off its surface. So that would probably be the case over here. Those photons were good enough for zinc, but they're not good enough for silver because silver required a larger amount of energy. But there's a second scenario. What happens if those photons were much better than zinc and they were just sufficient for silver? So if there were photoelectrons, so that's one possibility. So if photoelectrons are there, so if there are electrons, they will be slower than the ones of zinc. Now, let me explain what that means. Now, if there are photoelectrons, they would be slower than those from zinc because more energy would be used in getting them off the surface. So if there were photoelectrons, they would be slower than those on zinc. Because the reason for that is that zinc requires less energy would be used up to make those photoelectrons. So if there were photoelectrons, they would be slower than those on the surface of zinc because more energy would be used up in getting them free. Now, what about the surface of aluminium? So let's go back to our table. Let's just remind you about these. Aluminium requires even less than zinc. So if it's good enough for zinc, it's definitely going to be good enough for aluminium. So there will be photoelectrons. But now, since you need to use up less of your energy to get those electrons off, what happens? Those electrons will be faster than zincs. So that's exactly what's going to happen. So we're going to find that the electrons on aluminium are going to be much faster. So what we can say is that aluminium's photoelectrons will be faster than zinc's because less energy is needed to free them. So the electrons which come off the surface of aluminium will be faster than zinc. I want you to think about this. As I write this down, I want you to think about this picture. Okay? So aluminium's photoelectrons will be faster than zinc's because each photon has got enough energy to kick electrons off both, but zinc is much more difficult than aluminium. So zinc's electrons will be slower because there's not as much energy left over. Okay, so let's move on with this question. Okay, now it's asking us light of wavelength. Now here's where the equation actually comes in. Light of wavelength, so we're being told a wavelength of light, is shone onto a metal X. We don't know what metal X actually is. Now it tells me the average speed of the emitted electrons is that many meters per second. So these electrons are really flying very, very fast. So 4.78 times 10 to the 5 meters per second. Identify metal X by performing a relevant calculation. Now guys, this is tough. This is one of the tougher photoelectric questions that I've seen. And here's an indication of how many steps there are. 6 marks, guys. Incredibly tough. So the question is, where do we even begin? There's numbers all over the place. Now, Matrix, calm down, figure out what we've got, and figure out where we need to go. And the best way to do that is to say, okay, well, what type of question is this? This is a photoelectric effect question. So let's write down the photoelectric equation, Einstein's photoelectric equation. He said that the energy of a photon, when it strikes a surface, is divided up into 2 parts. It's divided up in doing some work to get the electrons off, plus the kinetic energy of the electron. So now kinetic energy of that electron. Okay, well let's figure out what we can do with this. Now we're told 2 parts to this. We're told a wavelength. Now wait a minute, a wavelength is a very, very handy way of finding out the energy of a photon. So we can figure out the energy of a photon. That's not too difficult. We can use the wavelength to do this. Can I find out the kinetic energy of an electron? Absolutely. Yes, we can. Because we've been told the speed of the electron or the velocity of the electron. So we can find out the kinetic energy of an electron. Now what that leaves me is the work function. I can figure out what the work function is. wait a minute, we've been given a table full of work functions. So hopefully the work function which I find will match up with one of these metals. And then we can figure out exactly which metal I shone the light onto. So now let's go about changing my equation in order to get my photoelectric effect and to get my work function. Okay, so the energy of my photon, how do I get that from my wavelength? We've been told that there's a wavelength of light over there, which is 2.3 times 10 to the minus 7 meters. Now guys, that is very high energy photons. Those are photons well into the UV band. In fact, those are in the UVB band. These are the types of photons which give you skin aging and skin cancer, and they do damage to the cells in your skin. They are doing the photoelectric effect inside your cells, kicking electrons out of your DNA. Now it says the light wave of wavelength 2.3 times 10 to the minus 7 meters. So there we go, we got wavelength. How do you get the energy of a photon from a wavelength? So let's look at my equation. And the equation which links up wavelength and energy is h multiplied by the speed of light divided by lambda over there. So hc over lambda. Now we've got our work function over there plus the kinetic energy of my electron. So what we're going to do is now we've got to go to our information sheet and find out how to get my kinetic energy of my electrons. So my kinetic energy of my electrons is a half times, now please make sure that this is not the mass of anything but an electron. So guys, I want you to go look there, familiarize yourself with the mass of an electron. So take a look down your information sheet, and then all of a sudden what you're going to find is that the mass of your electron is going to be 9,1 times 10 to the minus 31 kilograms. That is the mass of an electron. Then my velocity, the very high velocity over there, so there we go, velocity squared. So now I've got my mass of my electron, my velocity of my electron, okay, not anything else, and that leaves me with a way of finding my work function. Okay, so now this is a lot to swallow, guys. There's a lot going on over here. So what I've got to do is I've got to remind myself where all of this came from. So I've got my energy of my photon which came in, which struck the surface. There's my equation linking up the energy of a photon. So there we go. My energy of my photon is Planck's constant. You're going to have to find that on your information sheet, 6,67 times 10 to the minus 34. There we go. There's Planck's constant multiplied by the speed of light, another constant, which is 3 times 10 to the 8, divided by my wavelength, okay, which we've been given. So this is a lot of numbers, guys. You've got to be very, very good at using these calculations on your calculator. Then that's going to equal your work function, which is the energy that's required to get an electron off the surface of a metal, and then a half multiplied by the mass on an electron, 9,11 times 10 to the minus 31 kilograms, then the velocity of my electron, which is given to us at 4,78 times 10 to the 5 meters per second. Okay, so guys, huge amounts to calculate here. So what am I going to do first? Where am I going to go with all of this information? Okay, so now it depends on which information sheet you're finding, but my work function is going to be exactly the same. Doesn't matter which information sheet I find. So let's do a little bit of substitution over here. Let's first start off with this left-hand side. Let's start off with Planck's constant. Now, guys, a lot of you are saying, okay, now, well, can't I just work it out and put the numbers down, not show my working out? Guys, please show your substitution. Don't manipulate these, because if you do it wrong, your markers can't give you the method marks. So put in the numbers first, then manipulate. So we start off with Planck's constant, so let's start off there. So we're going to do that. So 6,67 times 10 to the minus 34 is my Planck's constant over there. Okay. And then I've got my speed of light. My speed of light is 3 times 10 to the 8. There we go. And then lambda, which is my wavelength of light. Now, please make sure that your wavelength, here we go, and that's the important part. My wavelength has got to be in meters, guys. Please, 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 please make it in meters. Okay, because absolutely, well, more often what happens is that my wavelength is given in nanometers, because this is 230 nanometers. I would need to make it into meters to make any sense. Please make sure that it's in meters before you go any further. So 2,3 times 10 to the minus 7. Lucky it's already in meters. So there we go. 2,3 times 10 to the minus 7 meters. Okay, the thing that I want over here is my work function. We'll get that out a little bit later on. And then on this side, this is the exciting part. Here we go. A half times the mass of an electron, so 9,1. Depends on which equation sheet you're looking at, but usually 9,1 or 9,11. I'm going to use 9,1 times 10 to the minus 31 kilograms. And then my velocity of my electron. Now, please don't forget to square it as well. So 4,78 times 10 to the 5. So that's a huge speed. Times 10 to the 5. And all squared. Guys, please don't forget your squared. So there's a huge amount of numbers. There's a lot to calculate here. And hopefully, my work function is going to come out to match something which happens a little bit earlier. So let's just go through where we got all these numbers from. I'm going to highlight them, and what I'm going to ask you to do is to calculate ahead of me, try to figure out which metal actually came out here. So let's do exactly this. So what I'm going to do is I'm going to highlight them as we go. So H, which is my Planck's constant, so there we go, times 10 to the minus 34 with a really long unit on it. 3 times 10 to the 8 was my speed of light, so there we go, we got our first two parts of my equation. Those are sorted out. My wavelength. Very important that it's in meters, guys, because very often it's in nanometers. Lucky for us, they had it already in meters in this question. Then, on this side, where did I get the mass from? Remember that this was the mass of that photoelectron. It's the mass of the electron which is coming off. And what else? I've got my velocity of my electron. There we go. So there we go. There are two numbers, the mass of the electron over here, and then my velocity of my electron. Don't forget to square it, please, because that's going to change your number tremendously. So there we go. Let's start substituting and starting to manipulate this, get my work function. Maybe if I've got a little bit of time, what I'm going to do is I'm going to show you how to work in electron volts. Okay, so let's do this all together. Let's do our substitution. So over here on the left-hand side, I've got to set up my energy of my photon. So there we go, 6,67. Now let me show you a really nice way of working with our scientific notation. Now the cool thing about these Casio calculators, and I love them to bits because they make my life so much easier. The nice thing about the one on your screen is I'm going to show you a button which is going to save you a lot of trouble. Here it is. It's right down in the bottom here. So I'm going to keep pressing on it for a little while. There we go. So times 10 to the x. Now guys, sorry, not twice. I'm getting a little bit too excited there. Right? Times 10 to the. Now whatever you put after that is your exponent of 10. Now we want negative 34. Now please don't say subtract 34. That's what the minus button on the right-hand side is for. If you look on your calculator, a good way to put in negative numbers is here on the left. There we go. Negative 34. Okay, so there we go. We've got Planck's constant in. What about on this side? 3 times 10 to the 8. So I push this button down at the bottom again. Times 10 to the 8. Close my brackets. And let's go down to the bottom. Again, let's practice using this number. And please, use this button. It's going to save you a lot of time, save you a lot of effort. There we go. Times 10 to the negative 7. There we go. We've got our energy of our photon. So let's just check out our energy of our photon. 8,7 times 10 to the minus 19. Now, if you look at your table, that's enough energy to get an electron off any one of those metals, guys. Please, that's way above any one of those work functions. So now what we're going to do is we're going to find out how much energy wound up as kinetic energy. So we are going to subtract the kinetic energy of that electron. So let's take that answer, let's subtract the kinetic energy, and we'll be left with the work function. So here's my energy of my photon. It's on your screen there, 8,7 times 10 to the minus 19 joules. That's how much energy the photon had. I'm going to subtract now the energy of an electron. So let's do this inside a bracket. So there's a half. So now my mass of my electron, so I say times by 9,1 times 10 to the minus 31. Okay, now this might get a little bit confusing. I'm going to put brackets around all of that, just to make sure that my energy of my electron, my mass of my electron is separate from everything else. I just want to make sure that nothing is changing on that exponent. Okay, I'll multiply by that. I've got this really long and complicated energy of my electron with its long velocity, so 4,78 times 10 to the 5, close my brackets, raise it to a power of 2. I've again got to close that outside brackets. This looks very, very complicated. Let's find out what my work function is. My work function is 7,66 times 10 to the minus 19. And that's sounding a little bit familiar, guys. 7, so I know that my work function is 7,66 times 10 to the minus 19 joules. That's sounding very close to one of the values in my table. So let's look up on my table. Let's find out, oh, wait a minute. 7,6 times 10 to the minus 19. It's very close to being silver, guys. Okay, some slight differences in information from your equation sheet or your information sheet, but that is pretty close. They are both 7,6 times 10 to the minus 19 joules, and that tells me that my metal must be silver. So there we go. Let me just run through the steps here before we take another ad break. So here we go. A light of wavelengths. We've got our incoming photon with that amount of energy is shone onto a metal X. We were trying to find out which metal it is. Now it says the average speed of the emitted electrons. There we go. We've been given a speed of electrons. Identify metal X by performing a relevant calculation. How did I know to start out with this? I started out with my photoelectric effect because I see electrons were coming off a metal. So what do? I write down Einstein's photoelectric equation. Here we go. The energy of a photon is equal to the work function plus the kinetic energy of the electrons. Okay. Now, I didn't have the energy of the photon. In fact, I've actually got none of these things. But I know that the energy of a photon can be calculated by Planck's constant times speed of light divided by its wavelength, and that gives me the energy of the photon which was coming in. On the right-hand side, that energy goes into two ways. Some gets used up to pull the electron off. Any extra energy goes into the kinetic energy of my electron. My electron's going to move off with that energy. Now, since we had the speed and the mass of my electron, that allowed me to calculate that part. Now, the next part was quite easy. All I needed to do was to go to my equation sheet, find out all of these values, substitute, and manipulate. So here we go. The rest is just a little bit of maths. So there we go. We had Planck's constant, we had the speed of light, the wavelength, remember in meters, and then on this side, now this might have confused some of you that were watching. There we go. That's the mass of my electron. Please go find that value on your equation sheet. And over here, this was the velocity of the electron. That was a little bit confusing as well, how fast the electron was actually moving. And then what we landed up with was a work function in joules. Now, this is an unbelievably small amount of energy. Now, it's not very common to work in joules when you're working in these small amounts of energy. So I just want to show you a little bit of a trick, and you might see this in some of your textbooks. It's how to work in electron volts. Here's the trick. This is the clue. Times 10 to the minus 19. That sounds very, very familiar. That sounds like the charge on an electron. So what I can do to change this into electron volts is actually divide. So what you do is you take your joules, your energy in joules, and you divide by the charge on an electron. So I'm going to take 7,66 times 10 to the minus 19 joules and divide it by 1,6 times 10 to the minus 19. And what this will do is actually get us a reasonable number to work with. That'll give us a number which is in something called electron volts. So there we go, 7,66 times 10 to the minus 19. So I'm using that number again. And I put this all over 1,6, which is the charge on an electron, times 10 to the negative 19. And I'll actually land up with quite a nice number here. So 4,79. So that tells me 4,79 electron volts. And when you're working in university and when you're working with the photoelectric effect, electron volts are actually a much more common way to talk about energies of electrons. And in fact, this is a way that you state the energy of even photons and talk about the minimum energies of photons striking skin. But before we move on, I think I'm going to give you guys a little bit of a breather. What do you think?
Yes, we should.
Okay.
Mindset says we are going to take a very short break. Do remember to post all your questions your answers on Curio. Go through the questions on Curio, answer them, and then don't forget to press the submit button, because that's the only way you'll see that your answers are right. And then if they're wrong, go through them, guys. Make sure you know what you're doing. Go over your mistakes and just check what you've been doing. Right now, though, we are going to take a very short break, so we'll see you straight after this. Welcome back, Mindsetters. We're still doing physical sciences with Phil. I hope you guys have been going through all the questions. I am posting as we go along on Facebook, so make sure you go onto our Facebook page. It is facebook.com/learnextra. The Twitterverse has been quiet, so please hit me up on Twitter as well. Ask any questions you may have and follow as we go along through the show. So Phil, let's take it away.
Thank you so much, Lenny. Okay, well, guys, as promised, we've dealt with a little bit of photoelectric effect. I'm loving some of the questions on the page. We've done some photoelectric, we've done some Doppler, and as promised, here we go, some diffraction. Guys, people don't understand diffraction very well, so we thought we'd take a look through a very typical question. Okay, so here it is, from February 2009, question 9, and this is obviously from paper 1. Guys, if you're looking, paper 1 is physics, paper 2 is chemistry. So here we go. Huygens' principle is used to explain the wave phenomena. Now, interference and diffraction. Okay, so here we go. We've got to state Huygens' principle. Now, please, guys, Huygens' principle is quite difficult to define and still get your full marks. Okay, so now, here's the points which your examiners are looking for when you define Huygens' principle. Now, most definitions are worth 2 or 3 marks depending on how complex they are and what words the examiners are looking for. So here we go. On Huygens' principle, now it says that each point along a wavefront, so each point along a wavefront acts as a source for secondary waves or wavelets. Okay, so now that's the first part of Huygens' principle. I just want to get this idea in your head before I write it down. Guys, I need a picture inside your head of what's going on inside Huygens' principle. He said that each piece of a wavefront acts as a source of secondary waves. Now, these waves move away from that disturbance or away from those points. So that's the entire Huygens' principle. Basically, what's going to happen is that each point along your wavefront is going to act like a new source of waves for secondary waves, and those waves will move away from the source. So those are the 2 points of Huygens' principle. So we've got to talk about points along a wavefront. So these points are along your wavefront. Now, it doesn't matter what you've defined as your wavefront. Your wavefront, remember, is just a line of particles which are in phase. So points along a wavefront act as sources for secondary wavelets. So there we go. So sources for secondary wavelets, and those move away from the source. For secondary, now they're looking for this, secondary waves which move away from the source. So secondary waves, now those come from those points and they move away from the source. So that's the last part. Now, what they do after that is they interfere with each other and make a pattern. But what we're looking for here is that semicircular shape, and that's due to diffraction. I saw you guys answering that on Curio, by the way, and it looks really good. So sources for secondary waves, and they move away from the source. Okay, so now there's Huygens' principle, and there's your 2 marks. Now let's get into the beef of Huygens' principle. And so now it says, use Huygens' principle to explain the diffraction of water waves in a ripple tank as they pass through a narrow opening inside a barrier. And here's my best explanation. So what happens inside this barrier? Let's just draw this barrier. So now I've got this barrier over there. Let's just make sure that we've got 2 parts to our barrier. So let's just clone that out. And let's have exactly 2 parts to our barrier. So here's my barrier, and there's a slit inside the barrier. Now we've got these wavefronts which are moving parallel to one another, and they're moving towards that opening between that slit. But now once they actually get inside, or at least past there, now there's my wavefronts. What I want you to notice is that each point along a wavefront, now this allows us to define Huygens' principle again. So each point along a wavefront is going to act as a new source for secondary wavelets. So what I'm going to do is I'm going to draw those in using purple. So what's going to happen is this one at the top is going to make itself a new wave. This next one's going to make itself a new wave. This next one's going to make itself a new wave. Now what do you see on the other side? What's going to happen is constructive interference will take place along a new and curved shape. So what I'm going to show you now is that my new wave over here, this is my secondary wave, which is made by all those secondary wavelets. So my first one over there what's going to happen is that these are going to move out and they are going to constructively interfere to make one combined wavefront. We're going to get a curved wave on the other side. What we're actually going to see is not the purple, but we're going to see the green, and there will be curved waves as they come out of here. Let's just make sure that that's in the correct place. So we're going to see these curved waves moving outwards from these nice straight waves which we're moving in. So these straight waves, as they move towards there, they're going to come out curved. And it's because of the interference. It's because of the interference of these secondary waves. And that is my Huygens principle at work. What's going to happen is that each point along that wavefront will act as a new source for secondary wavelets, and it's going to make those nice curved waves as they come out the other side. Now that's hugely important. But now what's happening over here is we're going to apply Huygens principle. So it says a slit, and this is where we're going to actually start to apply some calculations over here. Now this tells me that Huygens principle is used to explain the wave phenomena, interference and diffraction. We've dealt with that now. Now it says that a single slit of unknown width is illuminated with red light. So there we go. We've got red light over there. Now that means that that light is monochromatic of wavelength 650 nanometers. There's its wavelength. Calculate the width of the slit for which the dark band, so the first dark band, okay, will appear at 15 degrees. Okay, now you're saying, oh, dark bands. How do I don't have a calculation for dark bands. Okay, but what I do have is I have a calculation for the width of a bright band. So now let me explain what I mean. I'm going to draw out a picture quickly on what's actually going on here. So now, what happens when light goes through one of those slits? So let's just say we've got our slit over here, and light goes through. Now, light was originally traveling in a straight direction. So it traveled from left to right, and it landed on a screen. So let's just draw over here a screen, and what we're going to find is that there will be interference pattern on the other side over here. Now, what happens is that most of the light will go straight through and constructively interfere to give us a very, very intense band over there. Now, what I've drawn over there is an intensity graph. So it's very, very intense in the middle on that original straight path. So what I'm going to find over here is a very, very bright band over here. Then what happens is there's a dark band, and then another bright band, and then another bright band. And what we do is we find this as an interference pattern. So what we're looking for is actually how widely these things diffract. Now what they're asking us for is what is the angle that this light actually diffracts. So where will I find the first dark band? And that's what my second arrow is talking about. They're asking for that angle from the center to the outside of my first bright band. So now there's a bright band over here, and that is from constructive interference. They're looking for this position of a dark band. So there's my dark band, and they want to know what is the slit width through which I must have shone this light of 650 nanometers, which is red light. How wide was that slit if my angle over here is 15 degrees? Now there's only one equation which relates all three of these things, and that is your diffraction equation. Now guys, this is really not too difficult. So all I've got to do is say, okay, well, I'm not sure where to start, but I'm going to write down my equation, and that is a good start in itself. So sine of theta. Now, theta is the angle of diffraction of my first bright band, usually. Now, here's where it gets a little bit tricky. There's an equation which tells me m, wait a minute, that's a little bit confusing, m lambda over a. Okay, so what do all these actual equations mean, and what do all these variables mean? So m is the number of the dark band. They told us that it was the first dark band, so that's lucky for us. One makes nice numbers. What about lambda? Lambda is my wavelength. Now guys, please remember earlier on in the show, I told you that lambda has got to be in SI units. It's got to be in those standard units. So there we go. So 650 nanometers, how do I write nano? Nano means times 10 to the minus 9. Okay? And then on this side, A is the value, or at least the width in meters of the slit. What about theta? I've been given theta, and that is sine of 15 degrees. That's cool. Okay, now we've got to do, once we've substituted, remember substitute first, manipulate second, I know that A will equal 1 multiplied by 650, 10 exponent minus 9, that's my 650 nanometers, and then divided by sine of 15. Now this should be easy enough for our Casio calculator to handle, so let's do this together, let's substitute together, and we can practice using that button that I showed you a little bit earlier on. So we've got, let's just do this exactly as I've got it, so 1 multiplied by, sorry, let's just make sure that we've put this into a proper fraction. Let's go back to our top. So 650 times 10 to the minus 9, and then down at the bottom what I've got over here is sine of 15. So sine 15. That's fantastic. So what I'm going to do now is just push my equals button. Let's close up all those brackets. Push my equals button. You're going to find a really, really tiny number over here. What I'm going to find is 6,51 times 10 to the minus 6. So there we go. So my slit width, A, is equal to 6. Sorry, let's just make sure we've got that right. So that's 2,51. Sorry, I'm writing this down incorrectly. I hope you're shouting at me at home and listening very carefully. You spotted that. So that's 2,51 times 10 to the minus 6 meters. Don't forget your units, guys. They can deduct marks. So there we go. 2,51 times 10 to the minus 6 meters. Now that's incredibly tiny. That is 2,51 millionths of a meter. Now where would we find these sort of spaces? Now lucky for us in Johannesburg at the moment, we've got some really bright sunshine outside. If you start taking a look through fabric, you'll actually start to see gaps which are this tiny. Now what that means is that you will actually find diffraction of light. And the reason that light looks so strange through those tiny little slits is because of diffraction through those really tiny little gaps in the material. Fantastic, guys. I hope that you understood what was going on in diffraction, Huygens principle, the whole lot. When we come back, we're going to look at your curio answers and see what went right and what went wrong.
All right, guys, we are going to take another short break. Remember to submit your answers on Curio, guys, so that it can be verified wrong or right. And then after the break or during the show, Phil will go through the questions and see what's wrong, what's right, and help you guys through it. So we'll be back straight after this. Welcome back, Mindsetters. Like we promised, we are going to go through the Curio questions that you guys submitted on your Curio. So make sure you guys stay focused and you're watching now because Phil is going to help you with some of the questions. Phil?
Fantastic. Thank you so much, Leni. Okay, guys, one of the questions that we noticed on Curio that it's got a pass rate of around about 20%. This by far was the most confusing one. But now what I'm going to go through is I'm going to go through the multiple choice questions. And this doesn't mean all of you. Somebody has got 100% out there, and hopefully we can congratulate you live on air. Here we go. It says that the work function is defined as. Now, guys, the work function, W0. Now, you've fallen for the trap, guys. But now I'm going to explain why. Let's go through our options and see if they're right, see if they're wrong. So it says the energy of light, and that's a good start, that shines on a metal. Is that absolutely right? No, it's not actually. Because the energy of light that shines on a metal is the energy of the photon. Now that's either HF or that's HC over lambda. We calculated that earlier, that's energy of the photon. Some of you chose this option. But now, here's where a lot of you, in fact, 56% of you were going for option B. Now, this was the misleading part. It tells me the energy of a photon, and that's a good start because it is to do with the energy of the photon, that will cause electrons to be emitted. Oh, wait a minute. Will cause electrons to be emitted. And guys, you got all excited at that stage and you were saying, yes, I've got work function. This looks like the right answer from a metal. Here's where things went wrong. With a high kinetic energy. No, guys. When you've reached the work function, the energy of a photon that will give electrons to be emitted from a metal, there will be zero kinetic energy. When the energy of a photon is equal to the work function, so if these two, so energy of my photon is equal to my work function, then there's no kinetic energy. Those electrons won't move. So now this would be right if I said that from a metal with high kinetic energy would have been 0 kinetic energy. Then option B would have been correct. So option A was incorrect, option B was incorrect. A lot of you were choosing option B. In fact, most of you were. Now, option C is a little bit more confusing. It says the energy of a photon where the photon has a frequency equal to the threshold frequency. That's kind of interesting. Now that tells me the energy of a photon, okay, that's a good start. So energy of photon where the photon has a frequency equal to the threshold frequency. Now that's another definition, guys. The threshold frequency is the frequency which allows electrons to be emitted. Work function is equal to h. Sorry, let's just make a little bit of space there. I'm making an error there. Okay, so work function is equal to h times F0. F0 is the threshold frequency. Now guys, if your energy of your photon, so this could be your photon, if your photon has got the same frequency as the threshold frequency, that means that you are equal to the work function. And whoever got this right, guys, that's awesome. That's amazing. Very, very cool. Option C is the correct one. The energy of a photon, so that's h times f, where the proton has a frequency equal to the threshold frequency. So that's basically saying that my photon has got to have h times the threshold frequency, then you will be equal to the work function. And guys, this is an equation to work out my work function. Let's just check the last option. E is equal to hf. Now that's tempting. E is equal to hf. Now guys, remember that that's just my energy of my photon. It could be equal to the work function, but we can never be sure. So E is equal to hf, guys. It's not absolutely certain. So option C is definitely the best one. I think we should actually go and take a look at the curio page and let's actually see what people were getting right and people were getting wrong. Okay, so let's look at our percentages. Okay, so first of all, when a source of sound moves towards you with a constant velocity, you will notice that. Okay, now there were a couple of options. 44% of you got this correct. So let's take a look at my options and let's see which one was correct. The sound does get louder and the pitch gets lower. Absolutely not. Option B, the sound gets louder and the pitch gets higher. Well, yes, as something gets closer, the sound will get louder. The pitch will get higher because of the Doppler equation. And that's fantastic. That is the correct answer. Let's just analyze our last ones, C and D. The sound remains the same loudness. That's wrong. Or the sound remains the same loudness. Guys, option C and D can't be correct. As something gets closer, the intensity, the loudness will get higher. The amplitude of the waves gets more. Okay, so let's close that one up. Let's go to the next one, and let's see what people did over here. So when violet light shines on a metal surface, photoelectrons with 0 kinetic energy. Okay, now that should tell you something. Violet light is just strong enough to make the photoelectrons come out. So violet light has got just enough energy. Violet light is at the threshold frequency. Now it says, what will happen when a very bright red light shines on the metal plate? Now let's just make sure that we understand what's going on here. I just want to go back to this, and we need to understand the difference between violet light and red light. Okay, so what we're going to find is that the energy of violet light, which had just enough energy, is actually more than the energy of red light, because violet light has got a shorter wavelength. So that means that the correct answer is that no photoelectrons will be emitted, and that was option B. So quite a few of you actually managed to get that right. Okay, we've done the work function question. I think we've got time to answer question 4 again. So it says, when waves move through a small gap, the waves bend around the gap to form semicircular waves. What do we call this phenomenon? Most of you got this right. You were watching very carefully. There we go. The correct answer is diffraction. And just very quickly, let's answer question 5. When monochromatic red light shines through a small slit, a pattern of red and black bands will form on the screen. If the source of light is changed to a blue light has got a shorter wavelength, which means that the diffraction angle will be slightly lower. So what that means, that a pattern of blue and black bands appears, but the bands will be much closer together. And the way that I justify that is quite easy. What I can do to figure out the effect of wavelength is I can actually take a look at this equation. And if you look at this equation, it's actually quite easy to see the effect of both my wavelength and the slit width. My wavelength has got a direct effect on the angle. The smaller the wavelength, the smaller the sine angle, and there we go. Blue light will make a pattern which is much, much closer together. So I suppose, guys, I'm hoping that you understand your wave sound and light, and I'm going to hand over to Luni to close up.
All right. Guys, thank you so much for tuning in, and congratulations to Sashni Partha. You got all your questions right on Curio, so congratulations to you.
Absolutely.
You're quite a smarty pants for physical sciences, so gold star for you. Well done. Guys, thank you so much for tuning in and for joining us on the Saturday show. Make sure you go through everything, and we'll see you next time.